El Niño and La Niña are among the most powerful forces shaping the climate system, but they are not storms, hurricanes, or droughts themselves. They are phases of a single larger phenomenon, the El Niño Southern Oscillation, or ENSO, that alters ocean and atmospheric patterns across the globe. Understanding ENSO has become one of the most important missions for agencies like NASA and NOAA because the stakes are not merely academic. ENSO influences whether crops succeed or fail, whether tornadoes explode across the central United States, whether drought grips California, and whether typhoons slam into Asia with unusual intensity. The science behind ENSO is complex, involving the interaction of ocean temperatures, trade winds, jet streams, and feedback loops that span the Pacific Ocean. Yet scientists have made enormous progress in recent decades, aided by satellite technology, deep-sea buoys, and advanced computer models. What was once seen as an unpredictable quirk of nature is now being dissected with precision, allowing forecasters to warn months in advance of how ENSO might unfold and what it means for societies worldwide. At the heart of ENSO lies the tropical Pacific Ocean, the largest single influence on Earth's climate system. Normally, strong easterly trade winds push warm surface waters westward, piling them up around Indonesia and Australia, while colder water wells up along the coast of South America. This creates a temperature gradient across the ocean, warm in the west, cooler in the east. The warm western waters fuel thunderstorms and rising air, while the cooler east is marked by drier conditions. In a neutral year, this system remains in balance, maintaining relatively stable global weather. But when the balance tips, either toward a warming of the eastern Pacific, El Niño, or an intensification of cooling, La Niña, the entire global climate system feels the reverberations. Ocean temperatures shift, trade winds weaken or strengthen, jet streams bend, and storm tracks change. NASA and NOAA scientists emphasize that even small changes in average ocean surface temperatures, sometimes just 1 or 2 degrees Celsius, can unleash massive shifts in weather patterns across continents. One of the biggest breakthroughs in understanding ENSO has come from tracking these ocean temperatures with satellite technology. NASA's fleet of satellites, such as Aqua, Terra, and Jason series, provide continuous measurements of sea surface temperatures, ocean heights, and even subtle changes in salinity. Ocean height, in particular, is a critical metric. When warm water piles up in the western Pacific, the sea surface there rises by as much as half a meter compared to the east. Satellites equipped with radar altimeters measure these differences with centimeter-level accuracy, offering a real-time map of where heat is stored in the ocean. Combined with NOAA's network of TAO Triton buoys anchored across the equatorial Pacific, which measure temperatures at different depths, scientists can see not just the surface, but also the hidden subsurface layers, where ENSO often begins to form. For example, a surge of warm water below the surface, called a Kelvin wave, can travel eastward across the Pacific and erupt at the surface, signaling the onset of El Niño months before it fully matures. Without satellites and buoys, these silent shifts in the ocean would remain invisible until the consequences were already unfolding on land. The jet stream, a fast-moving river of air that circles the globe, is ENSO's atmospheric amplifier. ENSO does not create new storms out of nothing. It alters the pathways of storms that already form. During El Niño years, the subtropical jet stream strengthens and shifts southward, funneling Pacific storms into California and across the southern United States. This often means wetter winters in the southwest, stormier conditions along the Gulf Coast, and milder, wetter weather across much of the northern states. During La Niña, the jet stream behaves differently. It shifts northward, steering storms into the Pacific Northwest and leaving the southern US drier than normal. This explains why Texas and surrounding states often suffer drought during La Niña, while Seattle and Portland are drenched. NASA and NOAA researchers track these jet stream shifts with atmospheric sensors on satellites and with high-altitude balloon launches. Computer models then integrate this data to project storm tracks months in advance. Understanding these jet stream alterations is one of the keys to predicting how ENSO affects weather thousands of miles away from the Pacific Ocean. Storm intensity is another field of active research. Scientists have long known that ENSO influences the number and strength of hurricanes and typhoons. In the Atlantic, El Niño years tend to suppress hurricanes because stronger upper-level winds shear apart developing storms. Conversely, La Niña years create favorable conditions with reduced wind shear, often leading to more frequent and more powerful hurricanes, as seen in the record-breaking 2020 season. In the Pacific, the opposite occurs. El Niño can fuel more intense typhoons, while La Niña sometimes reduces activity. These opposing effects are closely studied by NOAA's Hurricane Research Division and NASA's hurricane tracking satellites. For policymakers and coastal communities, the ability to link ENSO with hurricane outlooks is invaluable. It allows them to prepare resources, plan evacuations, and anticipate economic impacts months before storms form. While ENSO does not determine the fate of any single hurricane, it sets the stage upon which storm seasons play out. The sophistication of ENSO science today owes much to decades of research. One particularly influential study is the work of Wang and Lee, 2009, which reshaped how scientists view ENSO's diversity. Before this research, El Niño was often treated as a single type of event. But Wang and Lee showed that there are actually different flavors of El Niño, each with distinct impacts. The classic El Niño involves strong warming of the eastern Pacific near South America. But there is also a Central Pacific El Niño, sometimes called El Niño Modoki, in which the warming occurs more in the Central Pacific. This distinction is not trivial. Eastern Pacific El Niños tend to produce stronger global impacts, such as torrential rains in California and drought in Australia. Central Pacific El Niños, by contrast, shift rainfall patterns differently, often affecting typhoon tracks in Asia and altering North American winter weather in more subtle ways. By classifying El Niños into these types, Wang and Lee helped forecasters explain why some El Niño years do not fit the expected pattern. For everyday viewers, this means that not all El Niños are created equal. When NOAA announces an El Niño, it matters whether it is centered in the east or the middle of the Pacific, because the consequences for US weather and agriculture can differ dramatically. To put it simply, Wang and Lee's findings remind us that ENSO is not a single switch flipping between El Niño and La Niña. It is a spectrum, with events that can vary in intensity, location, and global reach. This has enormous implications for forecasting. For example, farmers in Iowa may expect wetter conditions during a strong Eastern Pacific El Niño, but during a Central Pacific El Niño, the rainfall might not come, leaving fields stressed. Similarly, hurricane forecasters might lower expectations in the Atlantic during a classic El Niño, but a Modoki event might not suppress activity as strongly. This complexity underscores why NASA and NOAA continue to refine models and gather more data. They are not only predicting whether El Niño will occur, but also diagnosing what kind of El Niño it will be and what that means for the United States. Another aspect of ENSO research that NASA and NOAA emphasize is the feedback loop between the ocean and the atmosphere. Once an El Niño begins, the warm waters fuel thunderstorms that in turn weaken the trade winds further, reinforcing the warming in a self-sustaining cycle. The opposite occurs during La Niña, when strong trade winds enhance upwelling of cold water, reinforcing the cooling. These feedbacks make ENSO events last for months and sometimes years, as seen in the prolonged La Niña from 2020 to 2023. Tracking these feedbacks is critical for determining not just when ENSO will start, but also how long it will persist. For example, a short-lived El Niño might only modestly affect US weather, but a multi-year event can reshape global food production, water supplies, and even political stability in drought-prone regions. Satellite technology continues to revolutionize this field. Instruments like the Advanced Microwave Scanning Radiometer, AMSR, and the Gravity Recovery and Climate Experiment, GRACE, measure not only sea surface temperatures, but also changes in ocean salinity and mass distribution. These subtle signals provide clues about how heat and water are being redistributed by ENSO. Meanwhile, NOAA's supercomputers ingest terabytes of data from satellites, buoys, and weather stations, running models that simulate the coupled ocean-atmosphere system. The accuracy of these models has improved dramatically in recent decades, to the point where seasonal forecasts of ENSO now have skill up to 9 months in advance. This is a remarkable achievement when one considers the sheer complexity of the system. It gives farmers, water managers, and emergency planners valuable time to prepare. Despite these advances, ENSO remains a challenge to predict perfectly. Sometimes events fade unexpectedly or shift in character. For example, forecasts in 2014 suggested a strong El Niño was imminent, but the warming fizzled, leaving forecasters scrambling to explain the false alarm. This is why ongoing research is critical. NASA and NOAA are investing in next-generation satellites and deeper ocean monitoring to capture even more detail. Understanding the subsurface dynamics of the Pacific, the role of Indian Ocean interactions, and the effects of climate change on ENSO's frequency and intensity are all active frontiers of research. Scientists increasingly warn that a warming planet could supercharge ENSO, making El Niño and La Niña events stronger, more frequent, or more erratic. If true, this would mean that the storms, droughts, and wildfires already linked to ENSO could become even more severe in the decades ahead. For everyday viewers, the science of ENSO may seem abstract, but its relevance is immediate. When NOAA issues an ENSO advisory, it is not just a technical report, it is a roadmap of how the coming months may unfold. A predicted El Niño might mean that Californians should brace for heavy winter rains, that Midwest farmers should prepare for possible planting delays, or that Atlantic coastal communities might see fewer hurricanes. A La Niña advisory might signal a drier than normal winter in the south, a colder than normal season in the north, or heightened hurricane activity in the Atlantic. For businesses, insurers, and governments, these forecasts are not optional. They are critical tools for managing risk. And thanks to decades of research from NASA, NOAA, and scientists like Wang and Lee, these forecasts are grounded in a deep understanding of the ocean-atmosphere engine that drives our planet's climate. The story of ENSO is thus the story of modern climate science itself, a tale of hidden forces made visible through satellites, buoys, models, and human ingenuity. It shows how something as subtle as a patch of warm water thousands of miles away can shape the lives of billions. And it shows why investment in science, observation, and forecasting pays off, not just in understanding the Earth, but in safeguarding the communities that call it home. The deeper scientists look into ENSO, the more intricate its mechanics appear. At first glance, the cycle seems straightforward. Ocean warms, atmosphere responds, weather shifts. But the actual science is a symphony of feedback loops, teleconnections, and subtle interactions that link the Pacific Ocean to nearly every continent. NASA and NOAA teams describe ENSO as a coupled system, meaning neither the ocean nor the atmosphere acts alone. Instead, they dance in sync, each influencing the other in a cycle that can last from 9 months to 2 years or more. This coupling is the key to understanding why ENSO has such far-reaching power. When sea surface temperatures in the tropical Pacific shift, they alter patterns of rising and sinking air. That change in turn bends the jet streams thousands of miles away, changing rainfall in Africa, shifting monsoons in India, and steering hurricanes in the Atlantic. From space, satellites reveal these connections in real time, mapping cloud patterns, ocean temperatures, and energy exchanges across the planet. The ability to visualize this planetary-scale choreography is what makes modern ENSO science so powerful compared to even a few decades ago. One of the most fascinating aspects of ENSO research is how it reveals the planet's interconnectedness. Take, for instance, the Madden-Julian Oscillation, MJO, a tropical disturbance that circles the globe every 30 to 60 days. When the MJO interacts with ENSO, it can intensify or dampen its effects. Scientists have observed that the MJO sometimes acts as a trigger for Kelvin waves, those underwater surges of warm water that can signal the start of an El Niño. Similarly, variations in the Indian Ocean, known as the Indian Ocean Dipole, can either reinforce or counteract ENSO conditions. NASA satellites detect these oscillations by tracking cloud formation, rainfall, and sea surface changes. The result is a clearer picture of how multiple systems interlace, like gears in a massive machine. For the public, this means that ENSO is not a standalone switch, but part of a web of climate drivers that all shape outcomes in unpredictable ways. This complexity is why seasonal forecasts always include probabilities rather than certainties. Scientists can say there is a 70% chance of El Niño, but they cannot promise its exact strength or its precise regional impacts until the event is already underway. The role of subsurface ocean dynamics is another frontier where NASA and NOAA have made leaps forward. ENSO often begins not at the surface but deep below. Warm water pools in the western Pacific during neutral years, held in place by strong trade winds. But when those winds weaken, that heat begins to migrate eastward, travelling along the equator in the form of Kelvin waves. By the time this warmth reaches the eastern Pacific, it begins to rise, raising sea surface temperatures and altering global weather patterns. To the naked eye on a California beach, this change is invisible. But satellites and buoys see it unfolding months before the effects hit land. This is what allows forecasters to give farmers, water managers, and emergency services precious lead time. NOAA's Teo Triton Array, a grid of over 70 buoys strung across the equatorial Pacific, is critical for detecting these subsurface changes. They measure temperatures at multiple depths, feeding the data into supercomputers that simulate the Pacific system. These tools are so sensitive that they can spot early warnings of ENSO shifts before any clouds or storms make them obvious to the human eye. Jet stream research has also advanced significantly. NASA's Atmospheric Infrared Sounder, ARS, and other instruments track upper atmosphere winds, revealing how ENSO events distort these high-speed rivers of air. During El Niño, the southern jet stream strengthens, steering storms into the southern US and often soaking California. During La Niña, the northern jet dominates, funneling moisture into the Pacific Northwest while the Southwest bakes in drought. But the relationship is not static. Recent research shows that climate change may be altering the jet streams themselves, which could interact with ENSO in unexpected ways. For instance, if the northern jet becomes wavier due to Arctic warming, ENSO events may produce different weather outcomes than they did in the past. This possibility underscores the importance of continuous monitoring and updating of models. For the everyday person, the message is clear. ENSO is not just repeating history. It is evolving in ways that we are only beginning to understand. Storm intensity studies provide another layer of nuance. Scientists once focused primarily on rainfall and temperature changes tied to ENSO, but today they also examine how it influences the severity of extreme events. For example, researchers found that El Niño tends to increase the risk of severe winter storms along the US West Coast. Atmospheric rivers, massive plumes of moisture that unleash torrential rain, are more common and more powerful during strong El Niño years. In La Niña years, the concern shifts to the Atlantic hurricane basin, where warm waters and low wind shear invite explosive hurricane seasons. NOAA's hurricane hunters, combined with NASA satellites like GOES and TRMM, Tropical Rainfall Measuring Mission, have tracked these patterns for decades, building a dataset that confirms the link between ENSO and storm behavior. The takeaway is that ENSO is not only about averages, but also about extremes. It raises the stakes for disasters, making the wet years wetter and the dry years drier, the quiet hurricane seasons quieter, and the active seasons more dangerous. Wang and Lee's work continues to shape how scientists and forecasters interpret these findings. By dividing El Niño into eastern and central Pacific types, they gave the world a vocabulary to explain why some events break the mold. When a central Pacific El Niño occurs, the impacts on jet streams, rainfall, and hurricanes differ in subtle but significant ways. For example, Atlantic hurricanes are not suppressed as much during Modoki events, which explains why some El Niño years still produce damaging storms in the Atlantic despite expectations. NASA and NOAA have embraced this framework, incorporating it into forecasts and public advisories. When NOAA now announces the likelihood of El Niño, it often specifies whether it appears to be an eastern or central Pacific event. For everyday viewers, this detail helps explain why forecasts sometimes change mid-season, or why impacts vary from one El Niño year to the next. It is not a matter of forecasts being wrong. It is a matter of ENSO being more complex than a single label can capture. Perhaps the most important message for the public is how much progress has been made in turning ENSO from an unpredictable hazard into a managed risk. 30 years ago, predicting ENSO beyond a few weeks was nearly impossible. Today, thanks to satellite technology, ocean buoys, and improved models, scientists can often give reliable outlooks 6 to 9 months in advance. This lead time has profound implications. Farmers can plan crop rotations, governments can prepare disaster responses, and utilities can anticipate energy demand. The forecasts are not perfect, but they are powerful tools that save lives and money. And with continued investment in research, the accuracy will only improve. What NASA and NOAA are discovering about ENSO is not simply advancing science. It is providing society with a shield, however imperfect, against one of the most influential forces shaping our planet's climate. ENSO's story is also one of technological triumph. For centuries, civilizations noticed strange weather cycles tied to the Pacific Ocean, but could not explain them. Fishermen along the coast of Peru had long observed that every few years, warm waters appeared around Christmas, disrupting their catches. They called it El Niño, the Christ child. Farmers in Asia and Africa saw their rains arrive late or fail completely during the same years, but the global link was not understood. It was only in the late 20th century that modern science began piecing together the puzzle. Today, NASA's satellite fleets and NOAA's global monitoring systems have transformed ENSO from folklore into a scientifically mapped phenomenon. Instruments in space scan sea surface temperatures, detect rainfall patterns, and trace shifts in atmospheric circulation with a precision unimaginable a generation ago. This technology does not just confirm what is happening. It allows scientists to peer months into the future, issuing warnings that can save harvests, guide energy planning, and prepare communities for storms or droughts. ENSO has become a prime example of how science can take something invisible, the slow sloshing of warm water thousands of miles away, and turn it into actionable knowledge that directly improves lives. Yet, the closer scientists look, the more they discover how much remains to be learned. One pressing question is how climate change will alter ENSO. Models suggest that a warming planet could make both El Niño and La Niña more extreme, amplifying their impacts. A stronger El Niño could mean more intense floods in California and worse droughts in Australia, while a more powerful La Niña might fuel deadlier hurricanes in the Atlantic. But the science is not settled. Some models predict greater frequency, others suggest more erratic timing. What is clear is that ENSO will continue to interact with broader climate change, creating compound risks that societies must prepare for. This is why ongoing research is vital. Wang and Li's discovery of El Niño flavors shows that even within a single phenomenon, diversity matters. Future research may uncover even finer distinctions, patterns that explain why one El Niño year devastates crops worldwide, while another passes with modest disruption. The pursuit of these details is not academic curiosity. It is the front line of preparing for a world where climate risks are growing sharper. For ordinary people, the practical lesson is that ENSO is not distant science, but part of everyday life. If you have noticed higher grocery bills, erratic heating costs, or unusual weather in your hometown, chances are ENSO played a role. It is the silent hand shaping the odds of floods, droughts, tornadoes, and hurricanes. By translating the latest NASA and NOAA discoveries into everyday understanding, we can better grasp how interconnected our world truly is. Knowing that a warm patch of ocean thousands of miles away might mean fewer hurricanes, but wetter winters helps families, businesses, and governments make informed choices. It transforms uncertainty into preparedness. ENSO is both humbling and empowering. It humbles us by showing how a vast ocean system beyond human control dictates so much of our weather and economy. Yet it empowers us because, through science, we can anticipate its moves, adapt our actions, and lessen the damage. From satellite eyes in space to buoys bobbing in the Pacific, humanity has built a global network to track one of Earth's most powerful rhythms. Each discovery adds another layer of protection, another step toward resilience in the face of nature's volatility. The journey is ongoing, but the progress is remarkable. This is why continuing to follow the story of ENSO matters. It is not just about climate models or scientific journals. It is about how those discoveries filter down to the food on your table, the safety of your home, and the prices in your community. The more we understand ENSO, the better we can adapt. And the better we adapt, the more secure our future becomes.